Hello students, good morning. I welcome you all for today's session. Now this problem will be the last problem on columns. Now this is a very important problem from your exam perspective. Reason being, it is a combination of columns and beams. Right, so let us start with the today's video lecture. A column has an I section with equal flanges of 180 mm into 14 mm and a web of 252 mm into 14 mm. When the column is used as a simply supported beam with UDL of 30 kN per meter, maximum deflection at the midspan is 2 meters. Determine the safe load that the column can carry at its free end with its other end fixed. Take the factor of safety as 4 and Young's modulus as 210 GPa. Right now, according to whatever dimensions he has given to me in the problem, I have already constructed the I section. So for I section, you can just check out. We already know what is the flange and what is web. So these two upper parts are known as flanges, and the middle connecting part is known as web. The dimensions are known: 180 mm into 14 mm for equal flanges. So this is first flange and this is second flange. Both the flange will be having the same dimensions. Then you are having web. Web dimensions are given to me in the problem as 252 into 14 mm. So I have marked that. Now the main logic lies here. What he is telling is this is the cross section of the column, and the same column he is making use as a beam. So when he is making use as a beam, it is subjected to a UDL of 30 kilonewton per meter, and because of this load the beam is going to deflect. Right, because of the load being applied, which is in the form of a UDL, the beam is going to deflect like this. The beam is going to deflect. So this maximum deflection at the midspan is 2 meters. That is what he has given. It is a simply supported beam. Then the maximum deflection will be at the midspan. The value is given as 2 meters. Now the crack or the gist here in the problem is, if you calculate the length of the beam, it is as good as you are calculating the length of the column. Because try to understand, suppose if this is the column, it is having certain length and it is having certain thickness, right? Now the same column he has made use as a beam. He has kept it horizontal. So if you find out the length of the beam and if you are using it as a column, then the length will remain same, right? So that is the logic here. He has not given the length directly. Instead he has connected it to a beam, and using the data of the beam I need to calculate the length of the column, and then I need to use the end condition, take the effective length, and then I need to calculate the safe load. That is the procedure what I need to follow. So first let me find out the moment of inertia. So moment of inertia about x-axis, ixx is given by, so ixx is given by, let us say it is bd cube divided by 12 minus bd cube divided by 12. Now you may be confused by seeing this formula. Don't worry, it is a very easy formula what I am trying to tell you people. Now BD cube is the outer maximum rectangle which can be formed, right? Outer maximum rectangle that can be formed, that is Ixx is equal to BD cube. B is 180. D is how much? So this is the total depth of the outer rectangle. So 252 plus 14 plus 14. So 252 plus 28. So let me check out 252 plus 28. So it is 280. 280 cube divided by 12. So the maximum rectangle, whatever is possible, minus this small web. Right? So what I am getting? BD cube divided by 12 once again. Now B here in this case is 166. Right? Now try to understand what I am making here. I have taken the entire rectangle. In that entire rectangle I am going to minus this blank area. I'm going to minus this blank area. Then what I'll be getting? I'll be getting the dimension or moment of inertia about the x-axis for this I section. So here in this case B will be equal to 180 minus 14. 180 minus 14, and d cube is equal to 252 cube. 252 cube divided by 12. Right, so the maximum rectangle minus the empty space. Maximum rectangle, outer rectangle minus the empty space gives me the moment of inertia of the I section. So Ixx is given by, so we just calculate Ixx. Let me check out, it is 180 into 280 cube, 280 cube divided by 12 minus, so here 180 minus 14 is 166 into 252 cube divided by 12. So I am getting the value as 107.9, 107.9 into 10 raised to 6. So Ixx is 107.9 into 10 raised to 6 raised to 4. Right, so once if we calculate Ixx, we also need to calculate Iyy, because you know in Euler's formula we are going to use the least moment of inertia. So next I'll be calculating Iyy. So whatever dimensions you have taken previously, you need to just swap them. So here what I'll be getting here is BD cube divided by 12. So B in this case for the flange will be BD cube. B D cube is 180 cube divided by 12 plus, we are having once again BD cube by 12, 252 becomes B. D is 14. Now here I told you this is for the flange and the other one is for the web. So this is for the flange, this is for the web. Now we know that there are two equal flanges, right? Two equal flanges. That is the reason I multiply this by 2. So therefore Iyy is equal to, so let me check out what will be the value. It is 14 into 180 cube divided by 12 into 2. So I got some answer. Now here it is 252 into 14 cube divided by 12 plus answer. So I am getting 13.67 into 10 raised to 6. 13.67 into 10 raised to 6 raised to 4. Right. Now he has given the maximum deflection for a simply supported beam with UDL. So now we know that the maximum deflection for a simply supported beam with UDL is given by, okay, all these are standard formulas, you need to remember them. I have also given you the list in the chapters SFD and BMD, so you need to remember them. So this maximum deflection, if I just call it as Y, so it is given by 5WL raised to 4 divided by 384 EI. So here it is Ixx. So this is important. Which I you should take, that you should know, because it is beam. Everything will be with respect to x-axis because beam will be horizontal. So it is Ixx. Right. Now here in this case, what all things are known, I'll just write here. Y is given as 2 meters. So you can take it as 2000 mm. Right. Ixx I have calculated. E is given to me in the problem as 210 GPa, so you can take it as 2.1 into 10 raised to 5 Newton per mm square, right? And W is 30 kilonewton per meter, 30 kilonewton per meter. So W can be written as 30 into 10 raised to 3 So that becomes Newton, and meter is 10 raised to 3 mm. So what you get here is ultimately this and this are going to cancel, so it is 30 Newton per mm. Right. Next, I'll put all those values here. Other things are constants. L value is what I am interested in. So I'll substitute and find out the value of L. So what I'll be getting here is, okay, so there is a small correction over here, and that correction is very important. Here in this case, you just take this as 2 mm. This is not 2000 mm. He has directly given it as 2 mm. Right. So while just noting the problem down, I have made a mistake. It is directly 2 mm. Right. I'll correct it later. You to correct this, because deflection cannot be 2000 mm. Right. 2 meter deflection is highly impossible. So it is 2 mm. Sorry for the mistake. So this is how you need to trace out your mistakes, because the moment I saw this 2000 mm as a deflection, something cracked to my mind. So that so much of deflection is highly impossible. So I might have committed a mistake. So I just checked the question right now. So it is 2 meters has to be replaced by 2 mm. Right. The moment I saw the data, I got to know whether it is correct or not. So that should be your expertise or efficacy. Right. Now in this problem, I have taken it from a textbook and he has wrongly mentioned it as 2 meters. So you please make it as 2 mm. So then it is 5 into W value is 30 and L value is unknown, divided by 384. E value is 2.1 into 10 raised to 5 into IXX value is 107.9 into 10 raised to 6. Right, so therefore let me check out what is the value of L raised to 4. I'll correct this later. So L raised to 4 is 2 into 384 into 2.1 into 10 raised to 5 into 107.9 into 10 raised to 6 equal to divided by 5 into 30. So L raised to 6, I am getting it as 1.160 into 10 raised to 14. And so therefore L, how you get L is the fourth root of this. It is 4 root of 4 of answer. So I'm getting 3281.9. So I'll roughly take it as 3. It is 3281.9. So therefore L, I'll round it off to 3282 mm. 3282 mm. Right. Fine. Now once if you find out the L, the logic says the length of the beam and length of the column are same. So length of the column is also 3282. So for safe load, for a column with one end fixed and other end free, one end fixed and other end free, effective length LE is given by 2L. So it is 2 into 3282. So you can just check out into 2. It is 6564 mm. Now from Euler's law, you know that PCR, so PCR is pi square EI divided by LE square. So where I is equal to IYY. Now reason I'll write here, because IYY is less than IXX. Okay, whichever is the moment of inertia smaller, that moment of inertia you need to consider here. All the values. Therefore, PCR is equal to pi square. Value of E is 2.1 into 10 raised to 5. I minimum is 13.67 into 10 raised to 6. L effective square is 6564. 6564 the whole square. 6564 the whole square. So you just simplify this and check out what will be the value. So let me check it. Pi square into 2.1 into 10 raised to 5 into 13.67 into 10 raised to 6 divided by 6564 square. Right, I'm getting the load as 657.58 kilonewton. It is into 10 raised to 3, right? 657.58 kilonewton. So it is 657.58 kilonewton. Now he has asked safe load. We know that factor of safety is equal to crippling load divided by safe load. So if you want safe load is equal to crippling load divided by FOS, right? So therefore safe load is equal to 657.58. FOS given to me, the problem is 4. So if you divide this by 4, I'm getting 164.39. So therefore safe load is equal to 164.39 kilonewton, right? So that's it. That's the end of the problem. Meet you in the next session. Till then, have a nice day. Take care.